let me take a few minutes to talk about Unit 5, what I call Unit 5B, which is the energy aspect of 2D motion. And I'm going to begin with the energy associated with projectile motion. Now, by their very nature, projectiles go up and they come down, which means they have a change in Y, which means we are, or it is experiencing changes in gravitational potential energy. With a projectile, the velocity in the X is constant, but the velocity in the Y does change, which means, and this is where the kids, and you have to be careful, which means the overall velocity is changing. I'm going to talk about that in a second. And so as a result, we are experiencing a change in kinetic energy. Now, assuming we have a closed system, no air resistance, which is typically the situation, or always the situation, we're going to have conservation of energy. Couple of things. Gravitational potential is only equal to 0 at the ground. Kinetic energy is never 0. And this is where sometimes it gets a little confusing, and we're going to take a look at this later on. Keep in mind, kinetic energy is 1/2 mv squared. V is the overall velocity. The overall velocity, which is a vector, is made up of the vector component of the velocity in the X plus the velocity in the Y, and we have to square root those terms. Pythagoras comes into play. And because our velocity in the X is never 0, we will never have a 0 velocity. So we'll always have some level of kinetic energy. And I'm going to look at an example about kind of bringing this all together next. So, projectile motion example. Let's say we're throwing a projectile off a cliff. That's the path it takes. We throw it at some initial velocity, at some angle. I want to look at these points. I want to look at point 1, where we throw it. I want to look at point 2, which is at the peak, and I want to look at point 3, which is right before it hits the ground. So at point 1, we have gravitational potential energy, and that's based on the height of the cliff. Okay. We have kinetic energy, and that's based on the initial velocity. So I'm going to call that my initial velocity, my initial kinetic energy, and that's based on the overall initial velocity. This total mechanical energy does not change assuming we have a closed system. So this is our constant. Okay. At point 2, we're at some maximum height, and if we're at a maximum, and so this is an example of obviously throwing a ball off the cliff, but we can adapt it to almost any projectile motion scenario. Where point 1 is when the ball is thrown. Point 2 is at the peak, and so at point 2, our gravitational potential is a max because we're at our maximum height. If our gravitational potential is a max, our total is a constant, then we must be at our minimum kinetic energy, which means we're at our minimum velocity, which is true because if you go back to what velocity is, the overall velocity is the square root of dx squared plus dy squared. This is 0. The velocity in the y is 0 at the peak. And so our minimum velocity is just the velocity in the x component. Okay. it gets kind of confusing, and a common mistake is at the peak our velocity is 0. No, our y velocity is 0. We still have an x velocity, which means we still have some motion and some kinetic energy. That's often a confusing point. At point 3, which is the final point, which is right when it hits the ground, we have no gravitational potential because we're at the ground. The height is 0, which means we're at our maximum kinetic energy. Actually, the maximum kinetic is all the mechanical energy, which means our velocity is a maximum. And so again, we get the velocity term from the vx squared plus vy squared. Since x is a constant, our velocity in the y at this point must be at our maximum as well. Now, I guess there is the situation where if you throw it like this, these steps don't always apply, and it's going to actually just be the reverse. This would be 3, this would be 0.2, and this would be 0.1. But these three ideas can be applied to the situation. Let's look at another example now. Let's look at a more common example with motion, with 2D motion and energy, and that gets into circular motion. So when we're dealing with circular motion in the energy aspect, there's a couple of somewhat unique things to keep in mind of. If we're talking about uniform circular motion, now remember, uniform circular motion is horizontal. What's uniform is that we're dealing with a constant speed. That's what we mean by uniform. And the only time we can have a constant speed really is dealing with a horizontal. So something is moving in a horizontal circle. If it's moving in a horizontal circle, our change in gravitational potential is 0. If it's moving at a constant speed, our change in kinetic is 0 because our velocity is the same. And so we really don't have energy considerations with uniform circular motion. It does have energy, it does have a velocity, so it has some kinetic, but it's not changing. Since our change in energy is 0, there's no work being done on the object. So that's one aspect of uniform circular motion. Now I want to take a look at another example of an object moving in horizontal motion where it's not uniform, but it is moving in circular motion that should be able to qualitatively describe. We're going to take a look at horizontal circular motion, and the example I'm going to use is my example I use a lot. It's a tetherball. You know, growing up, I played tetherball in elementary school during recess all the time. Basically, if you're not familiar with a tetherball, it's a pole stuck into the ground. At the top of the pole is a rope. At the end of the rope is a ball. Two people. The object is, you hit the ball in one direction. And you want to wrap the rope around the pole in that direction. The other guy's obviously trying to avoid that, and so the idea is moving in a horizontal circle. And so let's say it's moving that way, but it's it's moving horizontal, something like that. Now, if you've ever done this, or if you've ever had a pole with a string on it and something at the end, and you gave it a swing around, what you might notice is that as the rope wrapped around the pole, the ball goes faster. take, you know, if you're not really sure what I'm talking about, take a stick, tie a string to it, tie the other string to like a tennis ball, and just kind of give it a whirl like that, and then hold it still. Just get the ball turning in a circle, and then hold it still. And as that string wraps around the stick, the ball is going to get faster and faster and faster as it gets closer to the stick. So if the ball goes faster, that means velocity is increasing. If the velocity is increasing, kinetic energy is increasing. The only way we can change an energy level is to do work. And so if kinetic energy is increasing, work is being done. And so the question is, if I just take something and get that ball spinning and get it moving around, and it's going faster and faster, and I'm holding everything still, but the ball's moving faster, where's the work coming from? Well, this is an interesting little question to ask. Okay, let's look at the ball going around the pole. Let's look at it from the perspective of looking down on the pole, and I'm going to draw it big just so it makes it easier to see. That's my pole. My ball is right here, and the ball is moving that way. The rope is from the middle of the ball to the side of the pole. That's where the rope comes from. The ball's motion is with respect to the center of the pole. So here's our tension. There's a component of tension that's parallel to the ball's motion. The ball's motion is that direction. And so there's a component of tension that's parallel. The parallel component of the tension is what's doing the work on the ball. And so this is a little bit of an interesting scenario that sometimes crops up, and it's a good question to ask to get the thinking juices going, and to say, you know, show them the example. Spin something around, let it speed up while you're not doing any additional work, and see if they can, first off, see if they can make this connection. The velocity is increasing, kinetic energy is increasing, work has to be done. If they make that connection, then that's huge. That's huge. If work is being done, there must be a parallel force. The only force present is tension, so there must be a component of tension that's parallel to the motion. And this is part of this whole course. They got to make these little connections. Even though it might not make sense, they still need to make these connections. Okay, let's take a look at a vertical circular motion with energy. That's a more common type of energy problem. Vertical circular motion. We looked at the examples before: Ferris wheel, roller coaster. Fine. Let's look at point A. Let's consider point B. Alright. So the object moves from A to B. And so we have to have a change in gravitational potential from A to B. And this change in gravitational potential is actually going to decrease since we're lower to the ground. We may or may not know how high point B is above the ground. Which means there's work being done, and this work is being done by gravity. So work due to gravity is being done on the ball. If gravity is doing work on the ball, but gravitational potential is decreasing, kinetic energy must be increasing. And so, again, assuming we have conservation of mechanical energy, so This is where understanding what the system is. And if the system is the ball in the earth, so if we have a closed system, and I'm starting to work on my and I know I'm going out of order, but I'm starting to work on my systems notes right now, and I'll talk about this a little bit more then. But if the system is closed, it's the ball in the earth, then we have conservation of mechanical energy. And so we just use our very nice UGI plus kinetic energy is equal to my final gravitational potential plus my final kinetic energy. So depending upon what the problem is giving us, this term, our final gravitational, might be definable as 0. That's if we have no reference to the floor level, there's no reason why we can't define this as 0. Fantastic. Which means all that energy at the top gets is now all kinetic energy at the bottom. And if we know the kinetic energy, and if we know the mass, then we can figure out the velocity. That can then get turned into a centripetal force type question, because mass and velocity, we know radius, we know how much centripetal force is required. Those are common problems. Let's look at some more aspects with an object moving in a vertical circle. So let's take another look at an object that should be moving in circular motion. That does not look like a circle, but let's work with it. This might be something, and this is a vertical circle, and this might be something spun by a string, or it could be the roller coaster going in a loop. It's a vertical circular motion with some radius r that we know. And let's take a look at point A. If the mass is at point A, a lot of times the question becomes the minimum velocity to maintain the circle, or to maintain the circular motion. And so in these types of cases, if it's an energy type issue, we might know the total mechanical energy. And if we know the total mechanical energy, kinetic plus gravitational potential, we define our gravitational potential at the bottom as 0. And so we know the gravitational potential energy we have. It's based on 2r. And if we know the mechanical energy, we can get the kinetic energy. Maybe we're just given the kinetic energy at point A. Either way, if we're given the mechanical energy, or if we're given the kinetic energy at point A, the velocity at point A can be determined, which may or may not be the minimum velocity. Sometimes they ask for the minimum velocity, then we know v, then we know kinetic energy, and we know gravitational potential, and we can convert that to the mass at point B. So now, let's say our mass is at B. And if we know the velocity at point A, we can get the velocity at point B by using the conservation of mechanical energy. Because what we know is all this kinetic energy, or all the potential energy at the top of the circle, all the potential energy at the top of the circle is going to get converted to kinetic energy at the bottom. And so we can, if we know this velocity to get that kinetic energy at point A, we can get the velocity at point B through conservation of energy. If the problem gets into some centripetal force at point B, and if once we get the velocity at point B, we can get and we recognize that the centripetal force is tension plus Fg. This velocity at point B is going to feed into our centripetal force at point B. We know the mass, so that gives us our force due to gravity. Tension is just going to be the centripetal force minus the object's weight. And so we can look at that type of problem, and we can figure out how much tension is required to maintain that circular motion. And if we're dealing with a string with a certain amount of that will break at a certain tension level, a lot of times that they throw that in there. And so when we're dealing with these vertical circular motion, a lot of variations with energy aspects come into play with that. So that's the energy aspects associated with two-dimensional motion, what I cover in Unit 5B. I hope that was of some assistance and some help. Good luck.